continue with our discussion on coherent states. So, the first point I'd like to discuss today is about the relationship between a coherent state, get alpha, where alpha is a complex number with some magnitude and some phase, of course. So if you plot this on a field quadrature diagram, this is x1, this is x2. We know that this coherent state is a circular blob on the field quadrature phase space, and this length is alpha. So what we would like to do, see now, is we'd like to find out the energy inside the coherent state. How much energy does the coherent state contain? Okay. For that, we already have lots and lots of different kinds of relationships. So, for example, we do know that the total energy inside an electromagnetic field, the integral of half epsilon naught E squared plus B squared over 2 mu naught, and we derived this relationship, which was given by 1 over 4 epsilon naught, the volume, and E naught squared. Right? So this is a relationship we already have in front of us, where the electric field is given by E naught sine kz sine omega t, where I have taken the phase in the electromagnetic field to be 0. Alright, so with this definition of Ex, field trapped inside a cavity, this is the total energy that we have in front of us. Now if you look at this phase diagram, and if I were to calculate the length of this distance of this mean point of this blob from the origin, I need to calculate alpha modulus for the coherent state. Now alpha modulus, of course, is going to be x1 squared plus x2 squared under root. Correct? So this is x1 and this is x2. Okay? So now we have various definitions for x1 and x2. We can express x1 and x2 in terms of q's omega over 2 h bar of q. x2 is 1 over 2 h bar omega p, right? So now x1 can be written in terms of p and q. We also know that our q is given by epsilon naught v over 2 omega square 1/2 E naught sine omega t, correct? And our p, which is the derivative here, is given by E naught over v 2 1/2 E naught cosine omega t, correct? Right, so this is our q, this is our p, this is our x1, this is our x2, and we also know that our u total is given by half p squared plus omega squared q squared. Correct? We have these relationships in front of us. So we take these values of p's and q's, put them into this energy, right? And then we replace E naught sine omega t. So we have a q here. We replace this q with an x1, okay, and this p with an x2, right? Finally, we determine this object alpha. So, according to this expression, our u total comes out as h bar omega alpha mod squared. Okay? So this is the algebra for you to do on your own, which really shows us that these two derivations for the total energy must yield the same results. Okay? So this also tells us that h bar omega naught alpha squared is equals 1 over 4 epsilon naught v e naught squared, and alpha mod squared is epsilon naught v 4 over h bar omega naught e naught squared. Okay, so this is really the distance of the coherent state from the origin. Okay, and this is also representative of the amount of energy stored inside this quantum state. And we do also know that if we inside this even critique. All right. Now we also do know that the total energy inside an electromagnetic field depends upon the number of photons. Okay? For any electromagnetic field, be it a coherent state, be it a number state, as many photons exist in the system, we just take the number of photons and multiply it with the energy of each photon, which is h bar omega. And remember, we are assuming a single mode field. Okay? So we do know that the total energy, which is given by h bar omega naught alpha mod square. When alpha mod square is given by this, it depends upon the electric field squared. This must equal h bar omega n plus half. Correct? Where n is the number of photons in the system. Now, if n is large, for a large number of photons, which means large energies, large number of photons, far away from vacuum, if n equals 0, then it's the vacuum state. I'll talk more about the vacuum state in a minute. So if we take n large, then this is approximately h bar omega n, where n is the number of photons inside the electromagnetic field. Now, if we have a coherent state, comparing these expressions yields the really nice result that the length squared of a coherent state on phase space equals the average number of photons inside the coherent state. Okay? This is like an average number of photons for large n. Okay? So you just compare this with this. Alpha mod square is the number of photons in the system. So more photons in the system, you're further away from this position on phase space. Okay, and the length of this vector, the length of the coherent state, the length of the phasor is the square root of the average number of photons.
So this is all resonance is a matter of electromagnetic.
So this is no order momentum, this is omega. Okay? So on a phase diagram, the length of this vector is given by the square root of n. And from here I can also calculate geometrically the uncertainty in the number of photons. So the uncertainty in the number of photons will be proportional to this length here. Okay, so from this expression, I do know that n average is alpha mod square. So let's do an estimate for delta n. Right? So an estimate for delta n would be, now n is proportional to alpha mod square. So this would be this distance squared minus this distance squared. And we know that the width of this circle is 1/2. Right? So an estimate for delta n would be alpha plus, now the middle point is right in the middle of this block, so this point will be 1/4 away from the centroid. So this is 1/4 squared minus alpha minus 1/4 squared. Okay, so this is an estimate for the uncertainty in the number of photons present in a coherent state field. Okay, so let's try to kind of expand this. This is alpha mod square plus 1/2 1/16 plus alpha by 2 minus alpha mod square plus 1/16 minus 1/2. Correct? So which is so the length of this vector is square root under root n, and the uncertainty of the number of photons in a coherent state is also square root under root n, where square root of n average, so this is the square root of the average number of photons in the coherent field. That's the uncertainty. So now if you study statistics, this kind of looks familiar. You have a distribution. So if I were to plot n here, and here I plot the probability distribution as a function of n, and I want to find out how many photons exist inside the coherent field. Now there's an average number, n bar, and the uncertainty in n, which is the weight of the distribution, is given by the square root of this average. This distribution has a special name. This delta n is n bar average. So the n bar average goes up, this becomes, the weight also increases. Such a distribution is called a Poisson distribution. This is a Poissonian distribution. And we can derive the uncertainty in another fashion as well. Okay, so is this clear? So now we have a coherent state. We know what the length of that coherent state is on a phase space. It's given by the square root of the average. And this square root of the average is also the width of the distribution. The uncertainty in the number that exists for a coherent state. By the way, the uncertainty for the number state is 0. For a number state, the probability distribution will just be a peak at whatever average we have. Okay. So the Poissonian distribution is spread out as compared to a Dirac delta function. And the coherent state has a property that its uncertainty is precisely equal to the square root of the average number of photons. Now, you have to kind of measure these histograms. And by measuring the histograms, which are counts that are received on a detector from a certain kind of quantum field, can you tell whether that light is coherent, squeezed, or what is it? Okay, so now I'm going to present an alternative derivation of the exact same result. And also precisely show that the probability distribution has the same form as a Poissonian distribution. Okay. Now, in order to do an alternative derivation, let's proceed in this fashion. Again, ये भी coherent state physically क्या correspond करती है? What do they really mean in the laboratory? So we'll have one or two more lectures on the quantization of the electromagnetic field. So now I'm going to present an alternative derivation, right? So I want to find delta n, say. Delta n I know is the average of this operator minus average of the number of operators squared, given the coherent state. Okay, so we do know that the average number is just alpha mod squared, right? Do know that. That's called as n bar. This is something we already know. Okay, let's calculate this number here. Okay. By the way, how can you calculate this? So this expectation value n can be calculated in this fashion: A dagger A get alpha bar alpha. Right? This is simply alpha mod squared. Correct? And this is just, by definition, this is just the average number of photons. Okay? So this is a neater, easier derivation using the ladder operators. Now let's calculate this object here. This object here is bra alpha, A dagger A dagger A. Okay. Okay. So when A acts on alpha, I get alpha. When this acts, I get alpha mod. So I get alpha mod squared, alpha A dagger. Okay. So now I do know that I have this object is alpha mod squared, bra alpha, get alpha, and this object in between is 1 plus alpha dagger A. Using the commutation relationship, this is what we get. So this becomes alpha mod squared plus alpha mod squared alpha A. Right, so this gives you another alpha mod squared. Right. So now delta n squared is this thing, alpha mod squared, 1 plus alpha mod squared minus the square of this which is alpha mod 4, alpha mod square, which is n. So the uncertainty is the square root of this. So I get exactly the same result. Alright? So the next thing is, what if I would like to find out the, so I now want to find out the formula that this coherent state actually is a Poissonian state, which means that the probability of detecting n photons satisfies a Poissonian distribution. So for that I want to find out the probability amplitude of finding n photons in the system. I take the coherent state and find its overlap with ket n. This will be the probability amplitude overlap of the coherent state with the number of n photons needed.
Can you please repeat the last point you said about the probability distribution? How
So-
this gives the Poisson distribution?
Why does this give it? So we'll find out what kind of distribution arises. Okay. So I want to find this thing. Okay. So now I know that this is bra n. I do have an expression for the coherent state in front of me. The coherent state is given by n a dagger delta E minus alpha mod square sum over alpha is for n.
Yes, sir.
Alpha
Over
is for n over n factorial
square root.
square root, right? From n0 to infinity. Right? So this is our expression for the coherent state. Now I want to change the variables, right? That means n prime. Okay, so now this really means that the overlap of a number state is a Dirac delta function with respect to n and n prime. So this only one of these values will be picked up. So I will get e raised to power minus alpha square over 2, alpha raised to power n factorial. Sorry. Okay, so this is a probability amplitude. I take the square of this to find out the probability of finding n photons inside the system. Okay, so the probability of finding n photons inside the system in a coherent state is given by this inner product square, is given by E minus alpha square e raised to power 2n factorial. But what is alpha square? Alpha square is n average. So this becomes e raised to power minus n average raised to power n factorial. This is a Poissonian distribution. This is how we define a Poissonian distribution. And go home, plot this distribution for various values of n bar as a function of n. Right? So the Poissonian distribution only depends upon one parameter, that is the average. A Gaussian distribution depends upon two parameters, the average and the width. Because for the Poissonian distribution, the width is the square root of the average. So Poissonian distributions are really important because when you have scarce events, rare events, the probability of occurrence of those events can be approximated as a Poissonian distribution. So a binomial distribution, a rare binomial distribution is a Poissonian distribution. Okay, so, and this also I'll talk about later when I talk more about experiments. I will also describe that this is the limit of short noise. This is a short noise limit, the quantum limit of detection. And if you go beyond this, if you do better than this, if you get rarer events than this, then you have sub-Poissonian light. So I'll explain more about this when we talk about detection. But the coherent state provides a nice threshold between quantum and classical. Poissonian distribution is a nice classical distribution. Okay? So now we've kind of explicitly derived that the coherent state is given by a Poissonian distribution. It gives a Poissonian distribution in the detection of the photons. Any questions? Yes, sir. Now, a little bit kind of recap of squeezed light. Now we know that it's possible, we've already derived the uncertainty relationship. For a coherent state, we have a circle. And we know that this uncertainty relationship should be satisfied for any light whatsoever. It's a fundamental relationship, it should be satisfied if the uncertainty principle is true. Okay, so the coherent light has a nice property that it's a circle on the phase space. So each one of these deltas is equal. Right, so this is half, this is half. But it's possible to still satisfy the uncertainty principle by letting one of these factors grow at the expense of the other. So these circles become ellipses. Okay. So if the major axis of this ellipse lies along the phasor, the axis of the phasor, then we have increased the amplitude uncertainty, or the number uncertainty, because alpha modulus corresponds to the average number of photons. So we have increased the uncertainty in the number of photons. Delta n has gone up, but the phase uncertainty has reduced. So the phase uncertainty is given by this opening, this angle here. Let's call this delta phi. This delta phi has gone down, delta n has gone up. So the phase has been squeezed. So this is phase squeezed, right? It's also possible to kind of have this major axis perpendicular to the phasor, or the minor axis aligned with the phasor. Yes, please.
So the diagram of this phase uncertainty is valid in a spherical axis, right? It's not valid in the axis of current axis. It will be valid in an axis which is spherical, right?
Yes. So otherwise the concept of phase, if not, I will show you other example. If not, you have to take the maximum spread of this angle. That will be an estimate of the phase uncertainty. Here it's nice because it's symmetric about this axis, so you can just find it. Here it's also nice. But if I talk about other examples, I'll give you an example in a minute. So this is an example of amplitude squeeze light. जी.
सर जो फेज होता है वो आपको बताता क्या है फिजिकली?
वो इलेक्ट्रिक फील्ड बताता है। मैं अभी उसमें बात वो इलेक्ट्रिक फील्ड बताता है। डेल्टा n और डेल्टा फाई के दरमियान एक अनसर्टेनिटी रिलेशनशिप है। ठीक है। तो जो डेल्टा फाई है is proportional to the it's a measure of the uncertainty in the electric field. You'll figure that out in a minute. ठीक है। But remember that the phase is a very elusive concept, a very hard concept to grasp it. And it does not necessarily have a direct physical meaning. You can only draw analogies between electric fields and phases, as I'm going to show in a minute. Okay, so this is an example of amplitude squeezing. Correct? It's also possible to have And in this case, it's also possible to define an uncertainty in phase, a sum delta phi. Possible to do that here as well. But if I were to squeeze in the x1 dimension, I will get something of this kind, right? This is an example of quadrature squeezed light. X1 squeezed light. It's neither amplitude squeezed, neither phase squeezed. It's in fact a kind of combination. And in this case, it becomes hard to define the concept of delta phi in a neat fashion. So what one could do is kind of use this as a measure of the uncertainty in phase. Okay, so you can have squeezing along one dimension, you can have squeezing along the other dimension, parallel to the x2 axis. And you can have all kinds of shapes as well, by the way, in arbitrary orientations. So squeeze light is not necessarily canonical, so that it's amplitude or phase or quadrature, it could be anything. So there is a squeezing parameter that can, and I'll give you a homework problem on this as well. A number state is an amplitude squeezed light in a sense that its amplitude is fixed. Its amplitude is fixed, so it gives you a narrow ring, a narrow circle, where this length now is simply n, the number of photons, 1/2, right? If we ignore the quantum, the vacuum energy, right? And the phase is totally uncertain, and there is no uncertainty in the number of photons. Alright? Now let's talk a little bit about electric fields themselves. Okay? And what I would like to do now is I would like to talk a little bit about the vacuum state. So this state over here, the coherent state, is a nice circle. This circle could be anywhere. So you increase the number of photons in the coherent state, this circle goes further and further away. For the vacuum state, this state just collapses, this comes back, comes down, and you will get a circle of the same size at origin. Now this field is called the vacuum field, the vacuum state, ket 0. Right? The average value of the electric field is 0, but the energy is not 0. क्या आपको सवाल था? अभी हम इसको और बात करें. The average energy is not 0, but the electric field has an average which is 0, and the energy lies in the fluctuation of the electric field. Only the fluctuation of the electric field. So these fluctuations are called vacuum fluctuations, and this energy is called the ground state energy. So let's talk a little bit more about this. Now I want to talk about fluctuation in the electric field. हैरत की बात है, देखिए मुझे बनती कैसे है, लाइट होती कैसे है, क्या बनती कैसे, कहाँ से आती है, ये करेंगे हम बात इस पर. ठीक है ना, हमें देखते हैं लाइट कोहेरेंट स्टेट्स हैं क्या, लैब में कैसे होती हैं, और स्क्वीज स्टेट्स क्या होती हैं. So let's talk a little bit about fluctuations in the electric field.
सर हम जाएंगे ना?
चल जाएंगे. Alright, so let's first of all talk about number states. Right? Ket ends. So first of all, let's find out what's the average value of the expectation value of this operator, Ex operator. So we know that the Ex operator, okay, so how do we find, so we know that we, अलजेब्रा है, बस मैं आपको थोड़ा सही करके दिखा देता हूँ. We know that the electric field Ex single mode is given by E naught sin omega t sin kz. We also know that this equals 2 omega square epsilon naught v 1/2 q sin kz. Correct? And we can put an operator sign on this. Okay? And we also know that this q is a sum of a and a dagger with a coefficient h bar over 2 omega. Right? So we do also know that this is 2 omega square epsilon naught v square root h bar over 2 omega square root. Correct? ये भी पता ना हमें. और ये q is a plus a dagger sin kz. पढ़े? ठीक है. Now this factor here this is 2 goes away, omega, there's an h bar omega, correct? This is my Ex. Check that. Correct? Fine. So now if I want to find the average of this, the expectation value of this operator in a number state, I just take the expectation value of this object in the number state. Now what's the expectation value of this in the number state?
Expectation of A plus expectation of A dash.
क्या होगी? Zero. This will be zero. Because n a plus a dagger n is zero. Right? So this is a lowering operator, this is a raising operator, is for lower कर देगा, इसका खत्म हो जाएगा, this is zero. So now in a numbered state, even though it has energy, the average value of the electric field is zero. Right? So energy है, लेकिन electric field की average value zero है. सिर्फ fluctuations है energy के अंदर. Okay? So now we want to really find out. So a pure number state. This is not a classical state, by the way. Remember, this is a number state. Something you haven't ever seen before. This is not classical states that you easily produce in the laboratory. These are not coherent states. For coherent states, this average is non-zero. But for number state, this average is zero. The electric field is zero. Now let's find out Ex squared, average of this, right? So I just take the square of this, which is h bar omega epsilon naught v sine square kz. Now I want to take the square of this. So draw n a square plus a dagger square plus a dagger plus a dagger a n. Okay? Now this term is going to give us nothing. This term is going to give us nothing.
एक नंबर हो गया
ठीक है? तो
फिर एक से n वन प्लस n आ जाएगा
1 plus n आ जाएगा ना बिल्कुल. So a dagger is 1 plus a dagger a. 1 plus 2n आ जाएगा. So I will get h bar omega epsilon naught v sine square kz and 1 plus 2n. 1 plus 2n. Correct? Or I can write this as n plus half. Wait. Okay, so this is my fluctuation again. Okay. Yes, please. Fluctuation in the electric field. So my delta Ex will be this minus the square of this. That will be under root 2 h bar omega epsilon volume 1/2 sine kz n plus half. This is a number strip. This is the uncertainty in the energy. Alright? Uncertainty in the electric field, sorry. Now let's look at this expression. First of all, this thing, I give it a new name. This will have dimensions of electric field. Right? So let's call this electric field per photon. Let's call it that way. Electric field per photon. So this is just a definition. This factor is, let's call it E omega. So delta Ex is E omega sine kz n plus half. This is the uncertainty in the electric field for number strips. Now if n equals 0, if n equals 0, then there is still some fluctuation in the electric field. That corresponds to the vacuum state. So if n equals 0, I put n equals 0, I will get E omega, this is 1 over under root 2. Okay, so 1 over under root 2 here.
फिर एक अंडर रूट उधर भी था
उधर भी था ना, लेकिन कोई बात नहीं, अब इधर आ गया, वो हमने उसको जम कर दिया इसके अंदर. So E omega and under root 2. Or sine kz. So this is the uncertainty in the electric field in vacuum. So this is for vacuum. So vacuum has some 0 point energy, which really means that there are fluctuations in the electric field. That fluctuations are proportional to E omega, to this term, h bar omega epsilon naught b. Alright?
फ्लक्चुएशन से क्या मतलब होगा
फ्लक्चुएशन का मतलब ये है कि भाई इलेक्ट्रिक फील्ड की एवरेज तो जीरो है, लेकिन वो इलेक्ट्रिक फील्ड उसके अंदर नॉइज है, ठीक है, जिसको हम शॉर्ट नॉइज कहते हैं। तो इसका ये मतलब है, और उसकी एनर्जी जीरो नहीं होगी, वो h बार ओमेगा ओवर 2 है, ठीक है। तो अब इसकी मैनिफेस्टेशन है, the vacuum state energy is real. So I'll give you certain examples that what happens when vacuum is fed into a beam splitter. If you have two plates that are placed inside vacuum, they will attract one another. This is because vacuum has energy. This is called the Casimir effect. Spontaneous emission, which was considered to be something that came out of the blue. There were two nice complementary processes in atoms. One was absorption, the other was stimulated emission. And they're complementary to one another. In fact, the coefficients were equal. But spontaneous emission looked like an outlier. There's no mechanism that describes spontaneous emission. It just happened. But spontaneous emission is actually stimulated emission by vacuum energy, by vacuum photons. Okay, so this is real. This vacuum energy is real. Yes, please.
इसमें law of conservation of energy violate नहीं हुआ?
कैसे?
कुछ भी नहीं है, वैक्यूम आ रही एनर्जी आ रही,
नहीं, कोई वायलेशन नहीं।
मतलब कि आपने देखा ना प्लेट्स,
ये तो क्वांटम मैकेनिक्स की, ये तो क्वांटम इलेक्ट्रोडायनामिक्स की खूबी है कि भाई ये वायलेशन नहीं हो रही। हाँ, मैथमेटिकली अननॉर्मलाइजेबल थ्योरी आपको एक मिल रही है, जिसको रीनॉर्मलाइज करने की जरूरत पड़ती है। इट्स एन अननॉर्मलाइजेबल थ्योरी बिकॉज इफ यू सम अप ओवर ऑल द मोड्स इन वैक्यूम इट विल give rise to infinity. If you sum up over all the possible omegas that exist in the system, it will give rise to infinity. So that's a problem with this theory. But it's this energy is real. Its value is known, right? So you can find out this value, h bar omega epsilon naught b, the volume of the cavity. Everything is known here. So it will have certain units in volts per meter. Okay. So let's talk more about this now. अच्छा, एक काम करते हैं, what I would like to do, sorry, for consistency, let's define this to be e omega, just this, okay? So this, all right. Now what we would like to do is so this is true for the number state. We have defined a vacuum state for the number state. It's a blob at the center. Okay. We still haven't kind of confirmed this, but we now know that vacuum has energy in it. Okay? जी please.
वैक्यूम में एनर्जी इससे हम मतलब प्रिफर करें कि जो इंसर्टेड है ये उसका देयर इज सम एम्पलीट्यूड dw which अगर उसको मॉड करें तो वो एनर्जी बनता है, तो उससे हमें क्या है कि इसकी मतलब एनर्जी नॉन जीरो है।
बिल्कुल। क्योंकि देखिए ना, if energy is proportional to square of the electric field, I put n equals 0 here. So there is some energy e omega. This is proportional to e omega. It's actually e omega square. It's the square of electric field. This is the square of e omega. And then if you want, you can also integrate over the length of the cavity. You'll get an additional factor of 1/2 if you wish to do so. G.
E omega तो इलेक्ट्रिक फील्ड है,
तो उसका square energy के proportional होगा. Now we would like to do exactly the same calculation for the coherent statement. कर सकते हैं? देखो, by the way, one thing I would like to mention here for the number state, if I take delta n, that's 0. Okay, and if I multiply this with delta ex, right? Uncertainty in the energy, and we know that electric field is x polarized. The uncertainty in the electric field multiplied with the uncertainty in the number of photons. Now we know that this is 0. Correct? So, according to the uncertainty principle, this must be true. This must be greater than 1/2 of the commutator of the number operator and the Ex operator. Expectation value. Average, right? So this is the uncertainty principle. And this will be a homework problem. So for the number state, this thing is 0. So the only way in which the uncertainty principle can be satisfied is that this thing is also 0. And for a number state, this will be true. So what you could do is you take this operator m, which is a dagger a, and find its commutator with ex. Now ex is something proportional to a plus a dagger. Right? So this is ex with some 3 factors here. Okay? Correct? G.
Why must this commutation relation be 0?
क्योंकि if the left hand side is 0, and this must be 0 has to be greater than or equal to 0. So this must be 0. And we can prove that this is true. So if I take this commutator, this is going to give us 0 in the number state. Okay, you can prove this to be true. Okay? So this is general. For a number state delta n equals 0. So for a number state, this is going to be true. And you can prove this. So now there is a complementary relationship between the number of photons and the uncertainty in the electric field. This uncertainty in the electric field is also a measure of the uncertainty in the phase. Okay? So we have a relationship delta n, delta phi must be greater than or equal to 1. So I'll talk more about this in a subsequent lecture, because if I start talking about the phase, then it becomes really convoluted. But please bear with me on this point. The second thing I would like to mention here, we kind of invoke the idea that in vacuum there are fluctuations, there is a non-zero variance of the electric field. And there is non-zero energy. Now, what happens for the coherent state? If I were to repeat the same calculation for the coherent state, so what I need to do now is I need to find out Ex. First of all, I need to find this thing out. Now, Ex is something that is simple to do. I take this expression. Let's find out the average value of electric field. So h bar omega E naught V square root, I call this E omega sine kz alpha A plus A. Okay, so this gives me alpha, this gives me alpha prime. Okay, alright. So this is E omega sine kz and alpha plus alpha epsilon, which is proportional to the real part of the complex number alpha. And if I were to put time factors into this, yes please. जब अल्फा इस पे एक्ट ए इस पे एक्ट होगा तो अल्फा आ जाएगा, ये एक्ट होगा तो अल्फा स्टार आ जाएगा. So this coherent state gives me a non-zero electric field. So there is some electric field. And if I do this properly means that if these operators are taken to be time dependent because electricity is time varying. So what I could do is I could take these operators to be time dependent. Okay. So let me try doing that for a minute. Okay. So because I want to also capture time dependence in this. So suppose, how do I find out the time dependence of A and A dagger? So from the Heisenberg picture of quantum dynamics, we do know that if I have an operator A and I take the time derivative of this operator, I get iota over h bar AHA, right? Correct. This is the quantum dynamics in the Heisenberg picture. So instead of looking at the evolution of the quantum state, we're looking at the evolution of the operator. Right? So this is just the Schrödinger equation. But it's called the Heisenberg equation because it's in the Heisenberg picture. So I just want to confirm the ordering of H in the operator. ऐसे ही है. मुझे को बता सकते हैं क्या है? ये प्लस इधर प्लस है कि माइनस है? देखा में ठीक है. चलो करके देखते हैं. So what is my Hamiltonian? I know what my Hamiltonian is. Suppose I want to find out d by dt of the operator A. The operator itself is now time dependent. So what my goal is to make this time dependent. So I want to make this time dependent. That's my goal here. So this thing is iota h bar. Now what's the Hamiltonian? The Hamiltonian is h bar omega A dagger A plus half. Right, so this is what I need to calculate.
सर उधर माइनस आता है.
इधर
यस सर.
चेक कर लिया.
यस सर चेक.
h और इसका माइनस आता है. ठीक है.
1 over iota होता है.
ठीक है. All right. So this becomes minus iota h bar minus iota omega commutator of A dagger A with A minus I omega A dagger A minus A dagger A. So this is minus one. This becomes I omega I think. I omega A. क्योंकि ये A को मैं कॉमन A dagger A, this is minus 1. So the time derivative of the A operator is iota omega A, which means that my A operator, if I solve this differential equation, this is A at time t equals 0, we just simply write as A e is what I plus omega t. Alright? So I just solve this equation, right? The derivative of this operator equals this. Okay. Likewise, the dagger of this will be A dagger, but I don't write a parameter, it means at time t equals 0. E minus I omega t. Alright? So when I insert these expressions in here, this acquires e raised to I omega t. This requires e raised to minus I omega t. So this becomes alpha mod cosine omega t. खूबसूरत रिजल्ट आ गया आपके पास जी
For the coherent statement,
हम्म
for the coherent statement, instead operators to time independent क्यों कर रहे हैं?
क्योंकि ऑपरेटर्स हैं ना टाइम डिपेंडेंट क्योंकि इलेक्ट्रिक फील्ड तो टाइम के साथ वेरी कर रही है
मैंने पहले क्यों किया?
पहले भी करके देख लें वो टाइम डिपेंडेंस इज गोइंग टू गो अवे बिकॉज़ ex is 0 anyway इसमें हमें टाइम डिपेंडेंस की जरूरत पेश आ रही है इसको प्रेजेंट करने के लिए वहां पे भी कर सकते हैं
यहाँ पे ex का average is not 0, explain.
क्योंकि देखिए ना असल में ये सारे जो क्यू ऑपरेटर्स हैं ना ये टाइम डिपेंडेंट है असल में बात यहाँ से दिस क्यू इज e naught sin omega t this q is actually time dependent so even for the number states we can use time dependence but it will not affect the result so you try doing that but for coherent state it's important because I want to show you a particular corollary or particular result so for a coherent state the average value of ex operator equals e omega sin kz and 2 times alpha mod cosine of omega t. A plus A star is, you take the real part of this, that's alpha mod cosine omega t. Correct? Class है हमारा. So now this is a coherent state. Now the electric field is varying in time sinusoidally. Perfect with the frequency omega. This is a classical oscillator. A coherent state is a classical oscillator. A pure laser whose electric field varies with time with a frequency omega with of course some amplitude and if I want to average over the length of the cavity then I can do that as well if I wish to do so. Anyway, so for fixed z if I plot this average value for a coherent field it looks like a very nice oscillator. So a coherent state is an oscillator. A pure electromagnetic radiation with sinusoidal variation with respect to time is a coherent state. That's what a real, perfectly pure, spectrally pure laser means. It just has one frequency omega, purely monochromatic. This is hard to achieve by the way. But that's not the complete story. Because we still haven't determined ex square. Let's do that in our next class. And when we determine ex square, we'll find out delta ex. And that delta ex is going to cause this field to have some drift as well, some uncertainty. This thing is called uncertainty in phase, which comes out because of the fluctuation in the electric field. So if you could do on your own before the next class, find out ex square for a coherent state and find out delta ex. You will notice that delta x for a coherent state is the same delta ex as for vacuum. So we'll prove this. So this is the vacuum state. This coherent state is simply this vacuum state displaced. Right? Okay? So I think the next instructor is waiting.